All right, in today's lecture, we're going to cover orbital motion and Kepler's third law. Um, so we're really only focusing on these last two parts right here. They relate the universal law of gravitation to circular motion to calculate characteristics of circular orbit, and that involves both Kepler's third law and orbital speed. So recognizing that we haven't done gravitational field lines for a uniform field and for a point mass, which is in a non-uniform field, but we will get to that when we look at electric field lines. We're going to start look at them together later. These equations are the same equations we've looked at before, so there's nothing new here. We're just combining these equations and finding different relationships due to that. So let's look at the motion of planets or moons in our solar system. It's important to note that most objects aren't traveling in a linear path due to the force of gravities that exist or electrical forces. There's always some sort of curvature going on to the motion. We tend to focus on linear motion first to help us first understand how does motion work in a simple system, and then we're getting more and more complex. So when we look at each of the planets and we start identifying the forces that exist on them, they're in space, so there's no friction, there's no air resistance. There's only the forces of gravity causing these things to be in a form of circular motion. We will definitely simplify our understanding of the orbitals because orbitals tend to be more elliptical. But for us to start off in a simple system, an ideal system, before we look at it at a more complex way, we just want to say that every planet and every satellite and everything's moving in a circular path. So what are the net forces acting on each planet? I'm going to kind of disregard the forces acting on the sun because there's a lot of them acting outward, and the sun kind of oscillates a little bit, but it's so massive that the majority of the motion comes from the Earth or the other planets. So there's definitely some forces acting inward. I'm also going to neglect or just kind of disregard the forces between the planets because technically there is a force going between these two planets, but those are kind of ever changing and much, much smaller than the forces coming from the sun due to the sun's massiveness. So we're only going to focus on a simple system of a star-planet system or a planet-satellite or planet-moon system and move forward with that. So when we look at those gravitational inward forces, we recognize that, hey, you know what, that's a centripetal force. So we have an object, let's say, well, let's make it green to make it seem like it's Earth, although I guess Earth is more blue. But so be it. So let's look at Earth's in this position. So there would be a net inward force, and that is the force of gravity. And we know that that is our centripetal force, so that equals MAC. So that is our net force going in. We can keep on going further and saying, well, we know the universal law of gravitation is Fg is equal to gmm over r squared, where big M is going to be like the mass of the star and little m is going to be the mass of the planet or vice versa. And we also know that the centripetal acceleration, if we look at linear speed, is v squared over r. So I can plug in my force of gravity gmm over r squared into there, and I can plug in v squared over r into my centripetal acceleration. And I would end up with a relationship that looks like this. So I know that my mass of my planet cancels out, and I'm left with, on my left side, gm of the sun divided by, and I'm just going to call it r squared, where r is the separation between the planet and the sun. Hey, and I've seen this before. This is g. This is our gravitational field strength, but we've also identified it to be acceleration due to gravity, which would make sense why that is v squared over r, which is our centripetal acceleration. So our gravitational field strength is our centripetal acceleration in circular motion for objects in orbits. So let's solve for v planet. Well, I can continue doing some cancellation. I can cancel out one of these r's with the 2 right there, and I end up with a v squared is equal to gm over r, and then my v is equal to gm over r, but the square root of this. And this is equal to our orbital velocity. And that's why I wrote in a little v orbit right there. What's important to note is that this orbital velocity, it does not matter what the mass of the object orbiting is. So the only thing that v orbit is proportional to is the square root of m over r. So m being like the large mass object is orbiting, and r, which is their separation. Like, object orbiting and large mass. And we normally say that it's orbiting around a large mass, because if their masses are somewhat close to each other in orders of magnitude, then they both kind of orbit around each other, and that gets more complex. So we tend to think that one smaller massive object, so a small mass, is orbiting around a larger mass. It's also important to note that the v orbit is not proportional to the orbiting mass, right? The little m. It's only proportional to the large m, so the mass that it's orbiting around. When we move forward, we're going to look at Kepler's third law. Johannes Kepler is a physicist and astronomer way back in the day. He came up with 3 laws about planets and orbital motion. And really, we don't really need to worry about Newton's first law or second law, and a lot of these have to do with elliptical orbits. But the third law is going to be useful, but we're going to apply it to a circular path, and where the semi-major axis, technically in orbits that are elliptical, there's a semi-major and a regular major axis, but we're just going to call this our radius in circles, because we don't deal with elliptical orbits. And this is the relationship that the square of the orbital period of a planet is proportional to the cube of the radius of its orbit. And let's see where we can plug this in, because it's possible in IB they might ask you to derive this somehow. And it seems like it's complex, but all you have to do is just combine the right equations. So it's important for us to know 3 things. 1, that A is equal to 4 pi squared r over t squared. And it's also important, hey, look, I see t squared right there. That must mean I need to use it. We also need to know about the gravitational force is equal to the centripetal acceleration, and we know the gravitational force is equal to this. So the first thing we've already done is we're going to connect these two and say m times ac is equal to gmm over r squared, right, where the little m's cancel. And we get centripetal acceleration. And so I get gm over r squared is equal to my centripetal acceleration. Well, we found that this is our centripetal acceleration, so I'm going to take this and bring it over here, bring it in, and I'm going to say the centripetal acceleration is equal to 4 pi squared r over t squared. Now you can kind of see we want to find a way to get from t squared is equal to something times r cubed. And I see an r squared in the denominator on the left side and an r in the numerator on the right side. So I'm going to multiply that over, and I'm going to find that gm is equal to 4 pi squared r cubed over t squared. And then I'm going to multiply my t squared over, and I'm going to divide my gm. So I get t squared is equal to 4 pi squared r cubed over gm. And this is our end goal. We have t squared is equal to something times r cubed. We get 4 pi squared over gm. And this is Kepler's third law. Because t squared is proportional to r cubed, where 4 is a constant, pi squared is a constant, g is a constant, and then capital M is a constant. So the mass that the object is orbiting around, this is because in the beginning, when we were observing the universe, we looked at our solar system. So the mass of the sun was a constant at that time. We're going to be able to look at more, different situations in which we are including other stars or other massive objects that things are orbiting around. But for right now, we're just going to kind of assume it's a constant in Kepler's third law. Or we'll have to, include it in the calculation later. All right, let's look at some example problems. We're going to start with the Earth that orbits around the Sun. We recognize that the Earth orbits around the Sun in 1 year, so one full revolution of our orbit is 1 year. So we need to find the time period when orbiting around the Sun. You might stay simple and say, well, I know that it's 1 year. But recognize that time period is always in the units of seconds. So we're going to have to convert the year to seconds. So I will have 1 year times, well, how many days are in a year? There's 365 days in a year. And then I know that in 1 day, there are 24 hours. And then in 1 hour, there's 60 minutes. And in 1 minute, there's 60 seconds. Now, this is a form of what's called dimensional analysis. We set ourselves up with our given, which is 1 year, and we start multiplying it by conversions so that we can start canceling out the units, days to days, hours cancel out, minutes cancel out, and then we're left off with seconds. So if I were to do this calculation, I get the time period of 1 full year to be 3.154 times 10 to the 7 seconds. I rounded just so I'm not writing too many numbers, but I'm going to keep it in my calculator and I'm going to use it later. And let's move to the next question. What is Earth's angular velocity? Recognizing angular velocity is omega, like a puffy W, and that's equal to 2 pi divided by the time period. So I'm going to say omega is 2 pi divided by 3.154 times 10 to the 7th. Recognize that although I'm using the rounded number, I'm using the actual number in my calculator. So my value for omega is still as accurate as can be, and I'm just rounding at the end. So omega ends up being 1.992 radians per times 10 to the negative 7th. Radians per second. That's very, very small angle per second, which makes sense because it takes a full year to travel around the sun. And then I'm going to keep on going and say, what is Earth's orbital velocity around the sun? And I'm given the mass of the sun, the mass of the Earth, and the distance between the sun and the Earth. So between the center of the sun and the center of the Earth. So we just came up with an orbital velocity equation where V orbital is equal to the square root of gm over r. And I have that information. I've got capital M, which is my mass of the sun, and r, which is the distance from my sun, from the sun to the Earth. So I want you to pause the video and solve it using this method, because I'm going to solve it via another method. So go ahead and complete this. All right, so if we plug these values in, we ended up with a value of 2.99 times 10 to the 4th meters per second, or 29.9 kilometers per second, which is pretty darn fast. So another process we can use is recognizing that we just solved for a time period, therefore we solve for an angular velocity, and we can do v equals omega r because this is an object in circular motion. And this is really just another way of taking 2 pi times r over time period, which we found the time period with 1 year, and we end up with 2.95 times 10 to the 4th meters per second. So about 29.5 kilometers per second. So it's pretty darn close. I think the reason why is we're actually missing We said a year is 365 days when technically a year is 365 and a quarter days. So that might have caused the difference between the 0.4 kilometers per second. But that's pretty good. So we have, since the beginning, derived an orbital velocity using centripetal acceleration or centripetal force equations. We have used what we know about circular motion and gravitational force to come up with Kepler's third law, stating that t squared is proportional to r cubed. But we haven't yet used this proportion in some sort of proportional reasoning problems. So we're going to do some practice with proportional reasoning, and we'll start with Kepler's third law to launch us into it. So the Earth's time period of a full orbit around the sun is this time period that we solved for. And we want to determine the new time period of a planet that has twice the radius of Earth in our solar system. So we can take this relationship and also signify that t squared divided by r cubed, let me write that 3 better, is equal to a constant. And if it's equal to a constant, then it should equal to another time period, let's call it like t2 squared divided by r2 cubed. So if we call it like t1 and r1, we know that the ratio is always equal to 4 pi squared over gm, especially when we're talking about the big M is the mass of the sun. And it's the same for both planet Earth and this new planet we're talking about. So if we're identifying a radius of Earth, let's call that RE, and then twice the radius of Earth, so we'll have another planet of 2RE. So we're kind of seeing these two as separate. We also are seeing that there is a time period on Earth, which is 3.154 times 10 to the 7th. And that must be this other time period, which we don't know, and that's what we want to solve for. So let's say time period of Earth and time period of, I don't know, we don't know what this is. So using our proportionality, I can start off with the ratio of my time period squared divided by my radius cubed is equal to the new planet's time period squared divided by its radius cubed. So I'll have t, the time period of Earth squared divided by the radius of Earth cubed, and that's equal to the time period of question mark squared divided by the radius of question mark cubed, whatever that new planet is. Well, I'm going to actually plug in some things here. One, we know what the time period of Earth is, and we know what the radius of the new planet is. It's 2RE. So I'm going to take our values and plug this in and say the time period of Earth is 3.154 times 10 to the 7th, and that is squared, divided by, well, my radius of Earth is cubed, that's fine, is equal to the new time period squared, which we don't know. I'm just going to call it t because we're kind of getting rid of these subscripts. And we have 2RE, which is now cubed. And now what's nice is I see RE is cubed on both sides. I can be able to cancel that. I know I can solve for my time period. So let's do 3.154 times 10 to the 7th and square that. I get 9.948 times 10 to the 14th. I still have RE cubed, and that's fine. And I end up with t squared is equal to 2 cubed, which is 8 RE cubed. And now I see RE cubed on both sides. I can cancel that out. And all I need to do is multiply the 8 over. So if I multiply, so I'm going to multiply by 8 as well. And that's going to cancel out that. Let's actually do it in blue. Times 8. And that cancels out this 8. And I'm left with time period on the right. So I have time period squared is equal to this number times 8. So I end up with 7.958 times 10 to the 15th, and I need to square root both sides. And to get time period is equal to 8.92 times 10 to the power of 1, 2, 3, 4, 5, 6, 7 seconds. And that is how we would solve proportional reasoning problems. This is one of the ways you can. I really like it when we know something's a constant, or a ratio is a constant, and we can plug this way. But there are going to be other examples in which I'm going to show you one way that I like to use in proportional reasoning problems. So here we have a gravitational field strength at the surface of the Earth is 10 newtons per kilogram. A planet has a third the mass and a double the radius of the Earth. What is the gravitational field strength at the surface of the planet? So step one, I would say, well, we know what the gravitational field strength at the surface of the Earth is. So we know G, which is equal to Gm over r squared. We know that's equal to 10. Now we have a planet that has a third the mass and a double the radius. So let's call this, let's call this G prime. And this G prime is equal to G, but it has a third the mass, so M, and let's maybe call this ME and RE. So ME over 3 divided by, and double the radius, so 2RE squared. So I know what the value of this is. So I want to look in this relationship and find where I can see those, right? I see a G, and I see an ME, and I see an RE. So we need to just solve for those and kind of factor those out of this. So I'm going to say, okay, this becomes G prime is equal to G mass of Earth divided by RE squared, but I have not forgotten about, let's do it in orange, my third and my 2 squared. So I'm going to write those outside as, well, it's 1/3 times 1/4, or let's just make this, 1/3 times 1/4, which is 1/12. So I'm just going to erase this and write 1/12. And I can say, hey, look, I see my GME over RE squared, and I can take my 10 and I can plug it in. And I get G prime is equal to 10 times 1/12. So it's equal to 10/12. And then, solve for whatever that is, 10 divided by 12, we'd have an acceleration. G prime is equal to 0.833 newtons per kilogram. So step one, identify our base equation. And then step two, identify what has happened to our new variables. And then factor out everything that is in the base equation so we can plug that value in. Sometimes we might not actually have 10. You might just have to plug G in. And we could also see this as, G times 1/12. So let's do another example problem, number 2. The magnitude of the gravitational field strength at the surface of a planet of mass m and radius r is G. What is the magnitude of the gravitational field strength at the surface of a planet of mass 2m and radius 2r? So we kind of have a similar problem going on, but they're not giving you a value of 10. So I want you to use the same steps I used in number 1 and try to solve for a value of a G prime in terms of G. Pause the video and complete this. And I ended up with a G prime value that's equal to 1/2 times G, which is different than number 1 where you actually found a numerical value. But both work depending on the situation. Let's move to number 3. As we move forward, I have one more problem to kind of walk you through because this one's a little weird, and then I want you to try to do number 4 on your own. So number 3, the gravitational field strength at the surface of Earth is G. Another planet has half the radius of Earth and the same density as Earth. What is the gravitational field strength at the surface of the planet? So first, we need to recognize G is equal to Gm over r squared. Nothing has changed there. But then it says another planet has half the radius of Earth and the same density as Earth. So we're going to have to see this as kind of two separate problems because they're not giving us a mass. If I were to write an equation down here for G prime for the new planet, I would end up writing capital G, and I wouldn't know what to put in my mass, but I would know that I would have r over 2 squared here. But it didn't give me a value for mass. It said it has half the radius and the same density. So we need to actually open up our minds to a new problem and try to solve for this new mass when it has a half a radius. So the density, which is referenced often as the symbol, like it's like a slanted P, also known as rho. So this is also called rho. And you'll see this throughout our learning in physics. This is equal to mass over volume. So another way of seeing this is, well, mass is equal to my rho times my volume, where this is density. And so we can recognize, and again, we have to take this into two steps. We have to recognize that we can solve for the mass of Earth using rho times the volume of a sphere, which is 4/3 pi, and the radius of Earth cubed. But we need to find our mass, let's call it mass prime, because all we know is this is rho 4/3 pi and then half of Earth's radius cubed. So when we see this, again, we have another proportionality problem where we see that the mass prime, the only thing different about it is it's the same thing as mass Earth, except it's divided by 2 cubed. So it's divided by 8, right? Because we see rho is the same, 4/3 is the same, pi is the same, and RE is the same. So what's different about it is that 2, and which when you cube it ends up becoming 8. So then, okay, we have our mass prime now. So we need to come over here and say, now I know what our mass is. Okay, it's equal to m over 8. So you have to be very aware if you see problems like that. Don't just assume it's m. You have to think about where does density come from? How do we use it? This is a harder problem. Definitely, maybe only shows up in the HL, but I can't promise you anything. So we're going to do the same thing. We're going to say, hey, it becomes G prime is equal to Gm over, let's see, here we go. So here I am being bad with variables again, r squared, but what's left over? Well, we have an 8 in the numerator and a 1/2 squared in the denominator. So I'm going to have 1/8 times, and since I have 1/2 squared, or 1/4 in the denominator, that's really meaning it's actually in the numerator. The 2 moves to the numerator, and that's 4. So we end up with G prime is equal to G times, again, 1/2. That just so happened to be the same as previously. All right, number 4 is the last problem I want you to try on your own. Or last problem I want you to try, and I want you to do it on your own because we're hitting the 30-minute mark. So go ahead and pause this video, attempt it, and I'm going to show my work in a little bit. The question is asking for determine the ratio of the time period of planet X to planet Y. So that's really looking for Tx divided by Ty. And I threw the mass in there just to confuse you because it's not necessary, because mass is not important for a planet. It's only important for what it's orbiting around. And since these planets are in the same solar system, it's a constant. So Tx squared divided by Rx cubed is equal to a constant, which is equal to Ty squared over Ry cubed. So I just set them equal to each other, and I plug the values. In. So first I set them equal to each other, and then I solve for Tx squared over Ty squared, and I plug the values in. I recognize that when I have Tx squared divided by Ty squared, that's equal to the square of Tx over Ty. I also plug the 1 and the 2 in, the 1r and the 2r in, ending up with 1/8 because the 2 gets cubed. And then I have to square root it, so I get t over ty, well, technically tx over ty is equal to 1 over the square root of 8, or 1 over the 2 times the square root of 2. So we have finished up. I'm sorry for this video being so long, but we started off with identifying that the gravitational force is equal to the centripetal force, solving for an orbital motion. It's not dependent on the orbiting mass, only depending on the mass that it is orbiting. We've used the same equations from centripetal force and gravitational force to derive Kepler's third law. And then we did a lot of practice problems involving the Earth in its orbit, as well as some proportional reasoning practice involving like IB style questions. So I will see you in class. I hope this helped. And a lot of this is just practice, practice, practice. So see you then.